Okay. Until recently, we have been talking extensively about stability for linear systems, especially for LTI systems. And starting from this hour, we begin to talk about the subject of controllability. Okay. At first, controllability and stability may seem independent subjects. Okay, they're not related to one another, but it's quite the contrary, because controllability is very close related to state feedback, and state feedback is, as we all know, is very closely related to stability, okay, of an LTI system. So, therefore, let's begin our study on controllability. Many of us have some idea on what controllability might mean, but it's always a nice thing to remember the very basics. Therefore, let's recall what controllability was over a simple example. Okay, consider the following second order system. Okay, x dot equals 0, 1, 0, 0, x plus bu, okay, ax plus bu. Okay. And controllability has nothing to do with the output part, y equals cx plus du. Therefore, we're going to concentrate on this piece of the linear system representation. Okay. Now, let's try to visualize these dynamics. Okay. And here is one possible way. So let x be the position of a boat, okay, and the boat is on the sea, and there are currents in that sea, okay. Okay, so suppose the input free terms, namely the AX term, represents the velocity component, okay, of our boat due to the currents. Due to currents. Okay. And the input term, or the BU term, represents the component due to the engine or the propulsion of the boat, okay, due to the engine or propulsion of the boat. Okay, now let's try to visualize these terms first separately, and then we're going to combine them in a single picture. Okay, so let's consider therefore the following scenario, case 1. The engine is broken, let's say, or we ran out of gas. Okay, so we have no input in the system, so we're left to the mercy of the currents. In other words, we have x equals ax for our dynamics only. Okay, so engines shut off. Okay, so that means we will now try to visualize how the boat moves according to the currents. Okay, so what we have is x1 dot, so x is x1, x2, okay, x is x1, x2, and x dot equals ax reads x1 dot equals x2, and x2 dot is 0. Okay, this is x2, and x2 dot equals 0. Okay, so x2 therefore is constant for all times. Okay, it equals its initial value, and the velocity of x1 depends on the initial x2. Since initial x2 same as x2 for all future times, so x1 dot is constant. Okay, so the velocity of x1 is constant. Okay, so let x1 represent the horizontal coordinate of our boat, and x2 represent the vertical component of our boat. Okay, or we can put some directions: west, east, and here we have north and south. Okay, and here this is the origin, and somewhere here is our boat. Okay, this is our boat. Now let's try to visualize the currents. So suppose that we start with initially on the horizontal axis, okay, namely x2 0 equals 0. Since x2 dot is 0, so that means if you start on the horizontal line, okay, you will always remain on the horizontal line. In fact, no matter where you start from, x2 will always be constant, therefore you will always be on that line where you start at. Okay. Okay. So if you start on the horizontal line, okay, where x2 is 0, x2 0 means since x2 dot is 0, x2 will remain 0 at all times, so x1 dot is 0 at all times. Okay, so x1 therefore is constant at all times. So if you start on this horizontal line, you will stay there forever. In other words, there are no currents on the horizontal axis. If you start somewhere, let's say above the horizontal line, somewhere here, so somewhere here means that x2 is something small, okay, and it's constant, so x1 dot therefore is positive. Okay, x1 dot positive means you're moving in the east direction. Okay, and the motion is determined by the constant current. Okay, so suppose that these arrows indicate the direction and magnitude of the current. Okay, if you start below the horizontal line, okay, but close to it, again this time x2 is negative. Okay, so that means x1 dot is negative and constant. The x1 dot is, the velocity x1 is constant. Okay, therefore you're moving this time to the west direction because initially x2 is negative. Okay. Okay. Now, what happens if you start a little bit above the horizontal axis? If you start somewhere here, again, this time x2 is larger, initial x2. That means x2 for all times is the same, that large value. And x1 dot is that constant. This time that constant is larger and positive. So that means, again, you're moving in the east direction, but faster, with a fiercer current. Okay, and likewise here the currents will take you to the west. Okay, and so on. And well, the picture is now more or less clear. That means the farther you start from the horizontal axis, the harsher, the wilder the currents. Okay, and if you're above the horizontal axis, the currents will take you east. If you're below the horizontal axis, the currents will take you west. Okay, and farther away from the horizontal axis, faster you move. Okay, so something like that. And here it's very fast. Okay, and same here. And so on. Okay, so then once again, now the picture is more or less clear. This is your boat, suppose. Engines are shut off, you're moving with the currents. Okay, so if you start somewhere here, you move along east. If you start somewhere a little bit above that line, again you move east but faster, and the reverse thing happens below the horizontal axis. And if you start exactly on the horizontal axis, there's no current there, so you remain where you are. Okay, so in a sense, all this line, horizontal axis, is a set of your equilibrium points for this system. Okay, now, so this thing is our current map. So the conclusion, therefore, is let's put the conclusion here. The boat moves along east-west direction due to currents. Okay, when we have no engine power. Now let's do the opposite thing. This time we're going to ignore the currents and try to figure out what happens if we give power to our engine, or what's the effect of BU term on the dynamics. Case 2, ignore currents. Okay, so this time we have velocity is determined only by the engine. Okay, equals BU. So in that case, what we have is x1 dot equals 0, x2 dot equals u, because the B matrix was 0, 1. Okay, so x dot equals 0, 1 matrix times u is x1 dot equals 0, x2 dot equals u. Okay, so what's going to happen is, so this is east, west, north, and south, and here is your boat. Okay, and here is the direction of the propulsion. Okay, so the rudder, in a sense, is broken, so we can only move in the north-south direction. Okay, so x1 that is 0, so that means x1 is constant no matter what you do with the input. So if you start here, the x1 component will not change, so that means you can only travel on that vertical line. If you start here, the x1 component should not change, so you will always move on that vertical line. And whether you're moving up or down is determined by whether you apply a positive input or negative input. And how fast you move up and down depends on the magnitude of the input that you apply. Okay? And now let's combine these two pieces together. Okay? So that's our general case. Let's call it case 3, where we consider both terms. Okay, x dot equals ax plus bu. So what we have here is the following: x1, x2. We have the current map, which becomes faster and faster as you move farther and farther away from the horizontal axis. And here somewhere is our tiny boat, and the input is in that direction or that direction. Okay. Now, let's, for this case, a boat on the sea with the current map like that and the rudder broken, and only we can move in that direction. if we use the engine power only, okay, on the vertical direction. Now let's consider the following question, which is closely related to the issue of controllability. Now this question is the central question in the issue of controllability. Given two sets of coordinates, okay, given two sets of coordinates, let's call it x initial and x final. Okay, so this is our starting point, and this is where we want to end up. And 2 times, 2 instance t0 and something later than t0. Okay, Monday and Wednesday, let's say. Can we find an input function u of t such that the boat can be steered to the final point, the destination, steered to x tf equals x final, starting from the given initial condition, okay, from x t0 equals x initial. Okay, and this question is closely related to the controllability. Namely, we have a state, we have a system x that equals ax plus bu, and then we have 2 points, starting point and end point, and we have 2 times t0 and tf. Okay, starting point and starting time and ending time. And then can we find some input function so that having started from the given initial condition and driving the system with that particular input, can we end up at the desired final position? Okay, if you can do that for all pairs, x initial, x final, and for all t0, tf, okay, and then we will call our system to be controllable. Roughly speaking, there will be some subtleties, but more or less, generally speaking, that's what controllability is. Okay, and now let's we will move on to 2 very important mathematical objects that we will use for our analysis in controllability. But before that, let's try to answer this question for our particular example, and let's determine whether our example is controllable or not. So we start at some point, okay, say here, and then we want to end up some other point, say here. Okay, can we do that? Okay, with for our system, let's see. Well, if you start at this point and if you want to go to that point, first of all, the currents are taking us to the left. Okay, so what we have to do therefore is, first we apply an input, positive input, so the boat will move up, and as it moves up, it enters the region where the currents are moving in the opposite direction. So it moves up, due to the input, it moves up, and once it has moved up, due to the currents, it's now moving to the right, and then once again, at some appropriate place, we can apply the input toward down, okay, a negative input, and that negative input will take us to our, well, if you do the computations right, to our final point. Okay, so it looks possible that to it looks possible that we can go from this point to the other point. Okay. Now, what if this is the difference between T0 and Tf is very small? Well, realistically, then there's not much we can do, but forget about the constraints, the real-life constraints. Suppose that we can apply enormous inputs, and the current speed can get enormous values according to this mapping. So if that is the case, if we accept that, then no matter how close Tf to T0, okay, let's say 1 millisecond, okay, just hypothetically speaking, we can still take the boat from this point to that point in the desired amount of time. How we can do that is as follows. You're here, apply an enormous input, and it will take you quite up, very up. And there, these currents are very strong. So very strong currents means that you will be carried to the right very fast. And once you're up there, you apply again an enormous input, this time negative, and that enormous input will almost instantaneously take you to the place where you want to be. Okay. So therefore, this system, from that point of view, is controllable. Okay, now let's introduce the following two useful objects, namely controllable subspace and reachable subspace. So the answer here is yes for our system. Controllable and reachable subspaces. Okay. Again, we're going to consider the general case, namely the LTV case, linear time varying case. Consider the linear time varying system. X that equals ATX plus BTU. Once again, controllability has nothing to do with the output part. So whenever we talk about our system, it's enough that we consider this part only. X that equals AX plus BU. Okay, so X is in Rn, so we're talking about an nth order system. And suppose that the input is represented by a vector of size k, whose solution x of t we know to satisfy the following: x of t equals phi t0 x t0. So this is the solution if we have zero input, if you set the input to 0, where this is the state transition matrix. Okay, state transition matrix times the initial condition. So that's the homogeneous part of our general solution. And if you have non-zero input, then you have also the effect due to the input, which is evaluated through this integral. T0 to t phi t tau beta u tau d tau. Okay, now having remembered this solution, now we're ready to introduce these two subspaces. Definition: reachable subspace. Given two times T1 and T0, T1 larger than T0 for our system x that equals AX plus BU, the reachable subspace this is the notation. R T0, T1 consists of all the states x1 Rn for which there exists an input T0, T1 to Rk. If there exists an input function that steers the state from the origin, okay, xt0 equals 0 to the point x1, okay. In other words, okay, reachable subspace for a given interval t0 to t1 is the set of points that you can steer the state from the origin to that point, okay, in this time interval by applying some proper input, okay. So x1 is in Rn. There exists an input function u such that x1 equals t0 to t1. Note that because we're starting from the origin, this term, the homogeneous part, just disappears. Okay, we only have that integral because we start from the origin, and then this t, the upper limit is t1, and then you pick all the inputs, okay, possible, and you compute all these integrals from t0 to t1 for all those different inputs, and for each different input you obtain a state, okay. So the set of all those states is defined as the reachable subspace, okay. Note that this is not a reachable, we're not calling it reachable set, but reachable subspace, because if you have 2 points that belongs to that set, their linear combination must also be, it's not difficult to see, must also be part of that set. Therefore, that set, reachable set, is indeed a subspace of Rn. Okay. x1 equals phi t tau b tau u tau d tau. Okay. Now, the sister definition is controllable subspace. This time, we want to end up at the origin, and then it's defined as the set of all points in Rn which can be steered by some proper input function to the origin through this interval t0 to t1. Okay. Definition of controllable subspace. Okay. Again, given 2 times, t1 and t0, starting time and end time, controllable subspace. Okay, this is notation C. T0, T1 consists of all the states x0 which can be driven to the origin, okay, for which there exists an input u t0 R0 to T1 to RK. That steers the state from xt0 equals x0 to the origin to xt1 equals 0. Okay. In other words, again, let's look at the general solution. This time, we start from a non-zero initial condition, okay, and where we want to end up at time t equals t1 is the origin, okay. So this time, the left-hand side is 0. So here we have 0, and then we want to solve the equation 0 equals this plus that integral, okay. For each, let's say, initial condition candidate. Okay, you pick an initial condition candidate, and then here we have 0. You try to solve this equation for input function u of t. If you can find a u of t, and then that initial condition is part of your controllable subspace. And then you pick another initial condition, check whether there exists an input that satisfies this equation where the left-hand side is 0. If there is, then that state also belongs to your controllable subspace. If it doesn't, it does not belong to your controllable subspace, and so on. So you collect all those points in principle, and then that set of those points makes your controllable subspace, okay? So here is a compact way of writing that controllable subspace is the set of all initial conditions Rn such that there exists an input such that 0 equals phi t0 x0 plus t0 to t1 this should be t1, okay, t1 tau b tau u tau d tau. Okay, so that's your controllable subspace. Okay, now later on we will define in a formal way controllability through these subspaces and also reachability, and then those two things will be the same thing for an LTI system. Therefore, we will be mostly using the word controllable. But before that, before formalizing our analysis, let's try to apply these two definitions to a simple example that we can sort of visualize. Okay, consider the following second order circuit. LTI. We have two RC branches connected in parallel as shown, and this combination is driven by a voltage source, and the voltage that's being applied is called U. So this is our input to our system. The state of our system, or the state variables of our system, are the capacitor voltages X1 and X2. Let this be C1, let this be C2. Capacitance of the first capacitor and capacitance of the second capacitor, and the resistances are denoted by R1 and R2. Okay. Now I is the voltage of the capacitor Ci. Okay, I equals 1, 2. Let's obtain the state space representation for this system, namely x dot equals ax plus bu. Let's figure out A and B matrices. So C1 x1 dot is the capacitor voltage in that direction, and that voltage is the voltage that flows through R1, because R1 and C1, they are in series. And what's the current going flowing through R1? It's the voltage potential difference between its terminals divided by the resistance R1, and the potential difference between its terminals is U minus the voltage of the capacitor. Therefore, we have C1 x1 dot equals U minus x1. So this is the resistor voltage plus minus divided by the resistance. Okay, and that produces x1 dot equals minus 1 over R1 C1 x1 plus 1 over R1 C1 U. Likewise, x2 that can be written 1 over R2 C2 x2 plus 1 over R2 C2 times the input of the voltage of the source, okay, which is our input to our system. Therefore, it was easy to write down x that equals ax plus bu equation for this system. Okay, so x that equals ax plus bu. This is our A matrix, this is our B matrix for this second order system. Now x1 dot, so for the first row we look at the first equation, x1 dot equals minus 1 over R1 C1 x1 plus 0 x2 plus 1 over R1 C1 u. Okay. Likewise, the second row is given by the second equation, which is 1 R2 C2, and here we have R2 C2. Okay, and that yields our A and B matrices. Okay, now let's obtain the solution for the system, which is easy because the A matrix is diagonal. Therefore, state transition matrix is or can be trivially obtained. And then once we have the state transition matrix, we can apply the definitions and figure out the controllable and reachable subspaces for this system. Okay, A diagonal immediately yields the following state transition matrix. E to the AT is e to the minus t over R1 C1 0 0 e to the minus t R2 C2. Okay, so that's our state transition matrix. Let's introduce the following notation. Omega 1 is the time constant corresponding to the first RC pair, and likewise omega 2 is 1 over the time constant for the other RC pair, 1 over R2 C2. Then we can write x of t equals e to the AT x0 plus 0 to t e to the A t minus tau b u tau d tau in the following form. So that equals x raised x10 and x20 are vector, and e to the AT is diagonal. Therefore, this will produce the following: e to the minus omega 1 t x10 e to the minus omega 2 t x20. Okay, so that's the homogeneous part. Plus we have this integral of state transition matrix times B, and that can be written as a vector of two separate integrals. The first integral is from 0 to t, e to the minus omega 1 t minus tau times the first entry of B, which is 1 over R1C1, which is omega 1. And then we have u tau d tau. And the second term, likewise, tau is omega to u tau d tau. Okay. Now we have the form expression for x of t in terms of our system parameters, and now we can determine the reachable and controllable subspaces. Now we're not going to make the general analysis. Let's concentrate on this special case where the time constants are equal. R1C1 equals R2C2, or omega 1 equals omega 2. Okay. Now we're going to consider the case with equal time constants. R1C1 equals R2C2, and that equals, let's call it 1 over omega. Okay, so under that assumption, let's rewrite x of t, which will become much simpler. Okay, so let's rewrite x of t. X of t equals what? Now this is e to the omega t now, and minus omega t, and this is e to the minus omega t. Therefore, these two terms are the same. Therefore, we can take it outside and multiply the initial condition vector simply by e to the minus omega t, the scalar. So e to the minus omega t times the initial condition vector. So in a sense, our state transition matrix can now be represented by a scalar, okay, informally speaking. And then we have the following integral. Okay, this omega 1 and omega 2, they are now the same, omega, and likewise here. So everything here is the same. Okay, this term and that term is the same. Therefore, what we're talking about is a vector that's in the span of the vector 1, 1, where both entries are the same. In other words, we can write this thing as omega from 0 to t, e to the minus omega t minus tau u tau d tau. Note that this is a scalar, and that scalar is multiplying this constant vector 1, 1. Let's call this equation 1. And let's call this function, which is a function of time, and that's determined by the input that we apply to our system. Let's call it alpha of t, okay, which is a scalar. Now, 1 implies the following: for the initial conditions, or for the initial condition x equals 0, that is, for the case where we start from the origin, for the case where the capacitors are initially empty, no charge, we have x of t equals alpha t times 1, 1. Okay. Okay. So what does this equation 2, imply? Let's figure out. And that equation 2, we reached under the assumption that the time constants are equal. Okay, R1C1 equals R2C2. Now 2 says that, let's consider only the first capacitor voltage, let's say, by choosing u of t, suppose that we can make alpha t whatever we want. So that means we can make the first capacitor voltage whatever we want, okay? Or just forget about the first capacitor voltage. Second capacitor voltage is what? Again, alpha of t. We can make the second capacitor voltage whatever we want. But what we cannot do is we can make this thing one thing and the capacitor voltage, the second capacitor voltage, another thing. So whatever the first capacitor voltage is, the second capacitor voltage must be the same. Okay? So geometrically speaking, 2 implies that for the initial condition x0 equals 0, we can never steer the state x of t to a point that is not on the line that's spanned by this vector 1, 1. Not on x1 equals x2 line. Okay, so let me quickly sketch a phase plane here. So this is our second order real space. Okay, this is x1, that's x2. And x of t, if you start at the origin, for any time t must be somewhere on it, depending on alpha t, but no matter what alpha of t is, you will always be on the line that's spanned by 1, 1. And 1, 1 means x1 and x2, they are equal to one another. Hence, we're talking about this line. Okay, so this is the x1 equals x2 line. And here, this is our starting point, namely the origin. And then solution. Once you start at the origin, the solution, no matter what input you choose, the solution must be somewhere on that line, because x of t equals some scalar times 1, 1. Okay. So that implies, by our definition, that the reachable subspace for this system, if the time constants are equal, is the subspace spanned by this vector 1, 1. Okay, so even though the system is second order, the reachable subspace is of order 1. Okay. Okay, so the reachable subspace for the system is, as we said, the line passing through the origin, and that's spanned by the vector 1, 1. The reachable subspace for the system, therefore R T0 T1 equals the subspace that's spanned by this vector 1, 1 for all initial and final times t1 and t0. Now how about the controllable subspace? Okay. Now let's also try to answer that question. How about the controllable subspace? Okay. Again, we have all we need. We have the general solution for our system under the assumption that the time constants are the same. Okay. So again, for equal time constant. And That's easy to figure out. From which points? Okay, so in order to be able to determine controlled subspace, we have to answer from which points can we transfer the solution or the state x of t to the origin. Okay, now equation 1 helps us to answer this question. Now what we want is, we want to figure out all these initial conditions x0, so that by some special u of t or by some special alpha of t, more or less they're the same, we have reached the origin, namely the left hand side is 0. So 1 implies, therefore, 0 is where we want to be at the end of time. Whether we can solve this equation for an initial state candidate x0 plus alpha t times vector 1, 1. Okay, now this is a scalar, e to the minus omega t, and alpha t is a scalar. Therefore, this equation means that x0 and this vector 1, 1 must be linearly dependent. Okay, if this equation is solved, and so that means x0 must belong to the span of this vector 1, 1. Okay, so this is our equation 3. Okay, equation 3 can be solved only for initial conditions x0 that belongs to the span of that vector x0 span of 1, 1. And then, by definition, this therefore must be our controllable subspace. Okay, so reachable subspace and controllable subspace, they are the same, and both are of dimension 1, where the order of our system is 2. Okay. Hence, the controllable subspace equals this one-dimensional subspace for all t1 and t0. Okay, and later on we'll see that if the time constants are different, omega 1 different than omega 2, then the reachable subspace and controllable subspace, they will be the entire space. Okay, R2.